First of all, in thinking about the past, I realized that it was 40 years ago when I first came here to Woods Hole to take the Neurobiology Summer Course, which was a 10-week, very intensive methods. And it was my transition, really, from being a theoretical physicist to a neuroscientist. And I fell in love with the place. In fact, I've been coming back every year since then, every summer. And first with Steve Kuffler, a postdoc advisor. We come here in the summer in this building when it was called Whitman and do experiments. It was wonderful because his friends would visit him continuously over the summer, and I got to know all the classical neurophysiologists. And then I organized the very first computational neuroscience workshop that was held here in the 80s, early 80s. And a few years later, Christoph Koch and Jim Bauer started the first summer course, Methods in Computational Neuroscience, which continues today. So this is ground zero for computational neuroscience, and I'm really pleased to be back. So this is the cover of a book that MIT Press will be publishing on October 9th. And I did not design the cover. I had no control over it, except the little tag at the top, Artificial Intelligence Meets Human Intelligence. And really, that's the theme of this talk. It's a story that goes back over 50 years, and it really covers a big part of the history of computer science and neuroscience. And I'm going to try to weave that together into a narrative. This book is really a narrative. It's really telling a story from my perspective of things that have happened. How did we get here today? What impact will it have on the future in terms of the new approach that has been developed over the last 5 years to artificial intelligence? So the story begins in 1956. So this is the year that a summer conference was held at Dartmouth. It brought together 12 computer scientists who started in the field of artificial intelligence. Now, look, if you think back to 1956, this is also a few years after digital computers were born. And so they were programming computers to solve mathematical theorems, play games like checkers. And they were convinced, and I actually have seen the application, that it would be only a matter of writing a computer program that would be able to perform as intelligently as a human, right? That was their goal. Now, they didn't care about the brain. They were engineers. They just wanted to build something that behaved like the brain. They, didn't want to be confused by the facts. But we'll see that, in fact, this led to a very interesting, sorry, and Marvin's going to pop up again. He has a couple of very interesting cameo appearances. So there's a story that went around when Marvin, he founded the AI lab at MIT. And the story went around back when I was a graduate student that their first grant proposal to DARPA, Defense Advanced Research Project Administration, was to build a robot that could play ping pong. Now, I don't think that there is such a robot yet today, but they were convinced they could build one. It turns out robots are even more difficult than other problems. But they got the grant, and they realized that they had forgotten to ask money to write a vision program. And so they assigned it to a graduate student as a summer project. I always thought that was an apocryphal story. But in 2006, I was at a meeting with Marvin. It was the 50th anniversary of that classic meeting at Dartmouth. And I asked him, is this a true story? He shook his head and he said, yeah, the fact's wrong. We did not assign it to a graduate student. We assigned it to undergraduates. And it turns out that in the archives at MIT, in fact, that backs this up. This is Minsky Papert, who's a collaborator with Marvin. The Summer Vision Project is an attempt to use our summer workers effectively in the construction of a significant part of the visual system. And it was thought that vision would be really easy, and it was intuitive. I mean, you wake up in the morning and you look out and you immediately recognize things and pick them up. what could be easier? That can't really be difficult. Well, it turned out that the intuition was completely wrong, and this is a way to illustrate it. And in fact, computer vision spent many decades trying to solve the problem. So, very non-trivial problem. So here's the problem. Now, it should be obvious to everybody here, not just Michael Fee. Is Michael here? Michael? He's not here. Okay. Does anybody else recognize what the bird is? Right, zebrafish. Okay. So, but it's obvious to you that these are two zebrafishes, right? I mean, finches. They're not, they're not looking at you directly, but it's clear from the markings that they have to be the same species. But it turns out because of the fact they're in different poses, means that if you have a simple template matching system that tries to superimpose them, it will always match another bird with the same pose better than these two birds. And so the task is to figure out for every object that you're trying to recognize, what are the distinctive features and the relationships between the features. And that requires a lot of labor. And computer vision was making progress. There's a very big data set called ImageNet with 20,000 categories of images, 20 million images. And the progress over the last few decades had been 0.5% per year reduction in the error rate, right? And that was because it took, to create a new category required a couple of man-years of work, because you have to not just recognize the object, but discriminate it from all the other 10,000, 20,000 objects. Now, we do that without any effort, and so it's really a mystery. How is it that the human and other species, and not just humans, but all these species that can see? Well, there's another approach that was started at about the same time, and this is a very interesting engineering kind of story. And the story is that the only existence proof that the problem of vision can be solved is the fact that nature has solved it, right? And so an alternative approach is to actually look inside the brain and see how it's done, right? Now, I talked to Alan Newell, who was another person who was at the Dartmouth meeting in '56, and I asked him, well, why didn't you, think about the brain? And he said, well, '56, not enough was known about the brain to help us, and we felt that we just had to carry on, and in fact, he did in his own research honor a couple of things, for example, that are relevant for the brain. The brain is very slow. These neurons that we have are really pokey. They're measured in milliseconds. Your cell phones go at gigahertz, right? That means 1 billion instructions per second. So they run rings around the brain. However, there are a lot of neurons, right? About 10 to the 11th, 100 billion in the human brain. But flies only have 100,000, and they see pretty well too. So, it's really a question of how to get those neurons working together. The other general principle is a high degree of connectivity. Each of the neurons in the cortex is connected to thousands of others, very densely connected. And in addition, and then this turned out to be the secret sauce for how to get brains to do really sophisticated things, plasticity. Brains are fantastically good at learning, and especially humans. We're champion learners. That's our special talent, special ability. We learn faster, we can remember more things, we have a big cortex than any other species. Okay, so the question is, let's just take the general principles and not worry yet about the details of how plasticity is organized or how the connectivity, but let's just look and to see what can be built out of units like this, simple processing units. Real neurons are actually much more sophisticated and complicated because they have to do all this on their own. They have to be autonomous. So there's an enormous amount of machinery in neurons. Now, about the same time that AI was getting off the ground, Frank Rosenblatt, who's on the faculty, a psychologist and engineer at Cornell, was developing a new approach based on learning. And here's a news announcement in 1958. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, right? Now here comes the hot part, the hard part. Reproduce itself. And conscious of its existence. I mean, I can imagine that came from his grant proposal, right? But the reality was that what he was proposing to do was something that he called the perceptron, which is very, it is the most simple embodiment of what a neuron can be. Okay, so here's the idea, that there's a bunch of inputs on the left here, and there's one output. This is a model of a single neuron. And there's two operations. The first operation is to take each of the inputs, multiply it by a weight. So weighted sum of all the inputs, sum them up, and if it's greater than some threshold, then the output should be 1, and if it's below threshold, it's 0. Now, just to be concrete, suppose this is an image, and each of these is a pixel, and if the pixel has some gray level, you multiply the gray level by some weight, and you sum everything up, and you put it through a threshold, and it's a discriminator. Now, here's what made this little simple model very powerful. So Frank came up with a learning algorithm for changing the weights through experience, through giving it examples of positive, something, for example, if you're trying to detect tanks, for example, in natural images, you give an example of a tank, and then if it gets it wrong, his learning algorithm was a simple way of changing all the weights so that it's more likely to recognize a tank in the future. And if you give it enough examples, it will converge, and it will be able to discriminate. And so this is a way of replacing all the labor that engineers would have to do in computer science to come up with the right features, because it would be able to learn the features from the raw data. So this was a real breakthrough, and I want to illustrate it just to make it concrete. This is actually from early, this is a simple problem of recognizing the sex from a face in which you've cropped all of the secondary sexual characteristics, okay? So here's an image, and I want you to tell me if you think this is an image of a male or a female. So if you think that it's a male, put up your hand. Okay, there's 1, 2, okay, how many think it's a female? Okay, you seem very confident. I mean, it's amazing. Can you tell me why? How did you come to this conclusion? Well, this is a real, it's really remarkable that we can do this without actually having any way of introspecting and finding out what it is. Now, here's a problem that we can ask the perceptron to solve, right? So what we do is we give this image and a bunch of others of males and females, and we use the perceptron learning algorithm, and we learn the weights. Now, we've represented the weights here by little squares, and if it's white, it's positive weight, and if it's black, it's negative, and the size is proportional to the area. And so this is a mask or a template you can put over the face, and it tells you which regions carry information about maleness, which is where it's white, and femaleness, which is black. So it turns out there's information all over, because this is a very broad and distributed source of summation. And so you're weighting, when you look at the face, it's like a gestalt, you're weighting all of this, and you come to a conclusion, and so does the perceptron. And in fact, it was about as good as people in my lab, after it had been learned up and then testing it on new faces it had never seen before. So this is actually a pretty good start, in the sense that it's doing pattern recognition, and it's doing a difficult problem, and it's telling us something. And it tells us that actually there's a lot of information about whether you're male or female in this region here between the nose and it's called a philtrum. It's very characteristic. It's the philtrum is much as you can see, it tells you that it's information that it's a male face. Okay. Now there's a fly in the ointment, and the fly is the fact that if you reduce this to 2 pixels and then characterize the values of the positive categories and the negative examples of the category, the perceptron can only learn to discriminate it if it can pass a line through the 2 sets of points. And unfortunately, most problems are not linearly separable. They are, and this is an example, you can't put a line through it and be able to separate the pluses from the squares. And this is a theorem that's proven by Minsky and Papert. back in 1969. And this put a stop to this whole line of research. It was impossible to get any money, support, to get a job. And that just basically meant that it was, all the resources were put into writing computer programs, rule-based, traditional, good old-fashioned AI. Now, what they did at the very end of their book, they say that, you know, if you had a multi-layer, if you had a generalization of the learning algorithm to a multi-layered perceptron that had layers of units instead of just an input and output, that this would be able to solve these problems. But in their opinion, no such learning algorithm would ever be discovered. So, you know, there was basically their intuition that was influential because, of course, they were wrong. But I'm really, my whole career wouldn't have happened if, in fact, the research had been done earlier. But there was a whole generation passed before a new set of fresh eyes look at the problem. And Jeff Hinton here on the right and I were convinced that we could crack the problem. This is actually taken here in Boston. This is my apartment in Brookline when I was a postdoc with Steve Kuffler at Harvard Neurobiology. And Jeff at the time was a postdoc at UCSD with David Rummelheart. And it was 2 years later that, as you heard from Xiaoxing, we solved the problem, or we came up with a counterexample. This is called the Boltzmann machine, and the units are binary. And the probability here is a sigmoidal function of the inputs. The idea here is you sum up the inputs, and instead of making it 0 or 1 if it is a sharp threshold, you do it with a certain probability that has a general curve, and it's 0 if it's very negative, and it's 1 if it's very positive. So here's a learning algorithm, and this is actually very elegant, and in some ways my really the paper that I really feel the most what's the right word? Proud. I'm proud of, in the sense that, thank you. In the sense that it solved the problem very elegantly. It just didn't solve it. It solved it very elegantly in a way that's biologically plausible. Why do I say that? It turns out that there have been many, many, many learning algorithms that have come subsequently that can solve multi-layer perceptron learning. Most of them are not very biological because they require you doing a lot of backward propagation of error or derivatives and so forth. But this one only uses Hebbian learning between pairs of neurons, between the input and the hidden units, and the hidden units and the output units, and between the hidden units. Same algorithm. And but what really convinced us that we were on the right track was that you had to put the network to sleep in order for it to get calibrated. So here's how it would work. You give it an input. You calculate the average correlations. How often were they on together at the same time when you have an input and output that you're trying to train it on? And then you turn off the inputs and the outputs, and you just let it free run, and it comes to equilibrium, and you compute the average correlation between every pair of synapses, subtract the two, and we demonstrated you could learn complex problems that the perceptron couldn't solve. But there were toy problems. These were problems that, you know, like the exclusive OR, which was a very simple problem, but it wasn't something the perceptron could do, and, you know, other problems that, that the perceptron couldn't solve. This could solve it. The only problem was it was very slow, and it was, let's see, that was 1983. So 30 years later, there was a very famous talk that was given at the NIPS meeting, Neural Information Processing Systems. It's been going on for 30 years. I'm the president of the foundation that runs it. And this one was actually held at Lake Tahoe. That's the gaming theme here, but also probability theory is important in machine learning. But there was a talk that was given by Jeff Hinton and 2 of his graduate students in which they demonstrated that on ImageNet, this big, difficult problem, that they reduced the error, you know, the one that had been going down 0.5% a year, by 20%. So it's as if you did 40 years of research. And almost overnight, almost all of computer vision now uses this technology. Now, so what happened over those 30 years? What happened was, number one, computers got 1,000,000 times faster. The learning algorithms got much, much better incrementally. People discovered how to regularize them. The problem is that with very large networks, there'd be hundreds of thousands of weights, and the danger is overfitting. If you overfit, it means you're memorizing and you can't generalize. The key is to be able to generalize to new images of objects that you've never seen before. And so they solved those problems, so there was improvements. And then there were many, many more images, many more examples that you could give it. And it was a combination of those three things that reached a certain threshold where learning and computers got cheap enough so that you could replace the engineers. You didn't need an engineer there to try to figure out what the features are. You could learn them from examples. And it turns out that what's beautiful about this approach, unlike the traditional writing computer programs, for a regular AI, you have to write a different computer program for every problem. You have to be a domain expert. But here, if you have the data, you can solve problems that are very difficult that otherwise would not have been possible with the very same algorithm, with varying the number of layers, varying some of the hyperparameters. And I want to give an example here. This now, at the top is actually the visual system in the monkey, and this is from a review paper by Jim DeCarlo. And on the bottom here is one of the most successful of the deep learning networks called the Convolutional Network. And I want to, first of all, show you that there's a parallel between what's happening at each one of these levels. So there's, in the case of the visual system, we know that the retina, it gets processed through a bunch of filters in the retina, get passed through the thalamus into primary visual cortex. And then there's a bunch of operations there, and then which are nonlinear, and that gets passed on to the V2, V4, up to the infratemporal cortex, and it's up here that you find neurons that are selective for very complex objects like faces. Down here, they respond to bars and edges and things that are simple features in small regions, but here you're recognizing the whole object. Well, so here is how the convolutional learning goes. The convolution basically is a linear filter that you pass it over all the locations in the visual field, and there'd be many of these features, but they're learned. They're learned by giving it examples of things that you want to discriminate. And there are several layers of these. Now, the transform, the nonlinear transform between them is a very simple one. In fact, they converge onto the very same architecture that you find in visual cortex, namely a linear filter followed by a rectified linear unit, a threshold, and then pooling, which means you take the same feature across a larger part of the visual field. This is called the complex cell. This is called the simple cell in the visual cortex. And then you normalize it, and that means you change the gain so that you're working within a limited operating range. And in the visual cortex, that's done with recurrent inhibition. Now, what I just described to you was what we knew about the visual system in the 1960s. And we knew it from the people who are standing here in this photo. Here's Steve Kuffler. Here is David Hubel. And here is Torsten Wiesel, when they were a lot younger. And it was Steve Kuffler who discovered, it was the first to record from single ganglion cells in cat in vivo, and described the two classes of cells, the most common types of cells that are carrying information in the cortex. One of them has an excitatory on-center and an inhibitory off-surround. And then there's a complementary one with an off-center and an annulus, which is excitatory. And he did this when he was at Hopkins. And if you know Steve Kuffler, you know that he was an electrophysiologist, synaptic. He loved synapses. And I once asked him when we were working together, why did you do this experiment? I mean, it was so uncharacteristic of what you did. And he actually had to build special apparatus, a dual beam ophthalmoscope, in order to be able to both have an electrode that was positioned on a ganglion cell. At the same time, he could move a spot around. So he had to be able to control it. And he said that, well, I was at the time at the Wilmer Eye Institute at Hopkins, and I was feeling guilty because I wasn't working on vision. So he did this classic experiment, 53, which is in all the textbooks, right? And he said, well, you know, I did my bit. So what he did was he had two great postdocs. He said, why don't you record upstream and see what you see up the road? And of course, that was David Hubel and Thorsten Wiesel. And that became their life work. And of course, they eventually won the Nobel Prize for it. I'm going to illustrate something that is, I think, a really wonderful way to imagine what it's like to transform the world into a bunch of spikes. Okay, so this is a neuromorphic retina that Toby Del Brooke developed, and it's really based on the simplest properties of these ganglion cells. Every pixel has two outputs, and a pulse is along one of the lines. There's a pulse every time the intensity increments by a fixed amount, small amount. If it doesn't change, then there's nothing. And then if it decreases by a small amount, the second line gets a pulse. So it's the on and the off, right? When it goes up and when it goes down. And here's what it looks like. This is a movie of what it looks like looking at now, this is Toby, he's moving back and forth. You'll notice that most of the pixels are gray. It only sends information when there's some of the change. And that's where all the information is that you're trying to recover from the scene, is where are things, where are the boundaries, where are the outlines. It's insensitive to filters, another great property. So it normalizes. And this is even more, I think, interesting. If you have a little spot that's going around in a circle, it's doing that at 200 times a second. A regular camera would only see an annulus because it's averaging over 30 or 40 milliseconds. But you can see here that the spikes from the leading edge and the trailing edge can be detected not by just looking at the relative timing of spikes coming. So this is a single spot, a single pixel, and this is what it sounds like driving through the streets in Zurich. Of course, what your retina is sending 1 million of these spike trains into the brain. Now, I want you to think about this. Right? You look out in the world, you see this fantastically rich visual scene. It's spikes. It spikes all the way up. There is no image in the brain. There's no TV set. There's no homunculus looking at it. It's just spikes, right? And that's what we're going to try to understand. That is the challenge. Okay, very, very quickly, this is, you just give you an idea of the scale. That's the pyramidal cell in the cortex. That's the microelectrode. Dave Hubel actually invented it. This is a simple cell showing you the excitatory and inhibitory regions. This is a complex cell. It's oriented, but it will give you a response no matter where the bar is in that little region called the receptive field. And now finally, this is the magic sauce for deep learning. The fact that we know that in the visual system, this is a retina down here, and this is primary visual cortex, there's like 12 layers of processing. Each one of them has a visual field. Each one is extracting different features. And these are the features that Jim DeCarlo recorded from the monkey and compared them to the features that are learned by deep learning and showed statistically that at every level, they had the same probability distribution, which means that somehow the learning that was going on in this artificial network was mimicking or recapitulating the actual statistical properties of the neurons at different levels, at different layers here, up to the infratemporal cortex. So now here's why that's important. It's not important, I don't think, just the performance. If you just look at the performance, that's not really what we're trying to do. We're trying to understand vision, right? Now, what Hubel and Wiesel did, and Dave Van Essen and all the others, basically just described what's there. But they didn't know what the simple cell was doing there. I mean, they guessed it was an edge detector. How do they know? I mean, it was all a correlation. These are all correlations. How do you know whether something is important or not? There are a lot of things there that may not be important for vision, for something else maybe. But Jan LeCun, who actually was the guy who put together the convolutional network here on the right, is an engineer. And what he would do is, over 20 years, he would fiddle with it and say, well, let's put in a, instead of a sigmoid, let's put in the rectifying linear unit, and it would improve it by 5%. Oh, let's put in the pooling and see if that helps. Yes, that helps by 10%. So in other words, he would have many, many, many things that he would do that he thought might work, and at the end of the day, he converges on exactly the same features that you see in the visual system. So this is more than recapitulating or just copying blindly what's in the brain. It's showing how each one of those features is contributing to the performance, right? And that gives you more insight than simply a correlation. It gives you insight about performance. Okay, here's a few examples for how this network works, deep learning. So this is an image that's never seen before, and here are its top 5 choices, and the one that is at the top is the one that has the most confidence. It's not terribly confident. You can see it's really confident this is a container ship. It thinks it's a mite. It might be a mite, but if not, some other creature. This is actually a pretty tough photo because it's secluded and there, a lot of other things going on, but it was pretty sure it was a motor scooter. And it also was pretty sure this is a leopard. But these are more interesting. Okay, you got this one wrong, right? Grill was number 2. It said it was a convertible. Well, who's right? I mean, this is a human label, right? Yeah, maybe the grill is the biggest thing here, but convertible is actually a very good choice. And now this is an example of where it knows more than most humans. Most humans would say these are mushrooms, but in fact, it's a particular kind of mushroom because it knows about 20 different kinds of mushrooms, right? And this is a funny one because humans picked out cherries, maybe because they were hungry, but the reality is that the Dalmatian dog is really much more salient, at least for dog lovers. And this is one where it gets the label is completely wrong. This is not a cat. Does anybody recognize what this creature is? It's from Madagascar, but it's not a cat. What? Yes, it is a lemur. It is, in fact, a ring-tailed lemur. And it didn't have lemur amongst its the trained categories, but it thought it was some kind of a monkey. It's not a monkey. It's a lemur. Okay, but it was actually much closer than the human who had put this label on it. Okay, now every year since 2013, there has been a blockbuster. That is, somebody has come up with something new, and typically what they add is a new feature from the brain. For example, AlexNet, which is the one that did this big breakthrough, was feed-forward. But then they put in recurrence. They put in feedback. And now they could do sequences. And so here they took the output from AlexNet, they passed it through a recurrent network that would spit out a sequence of words that would describe the picture. So this is picture captioning, right? Which is, it's pretty, this is language processing. So let's see what it did. Okay, it had this picture, and the top choice for the caption was a group of people shopping at an outdoor market. Now, this is not just a good caption, but it's actually linguistically correct. In other words, it has learned what a sentence is. It has learned how to put the words together in the right order. This is kind of a miracle. I don't know. The fact that these networks were able to scale up and with recurrence perform linguistic tasks at this level is something that surprised everybody. So here's a couple more examples. A woman is throwing a frisbee in the park. Now, in this particular network, not only does it give you the caption, but for each word, it tells you which part of the picture it's picking it up from. And you can see here that it has put the spotlight of attention right there on the frisbee. A dog is standing on the hardwood floor. There's the dog. A stop sign is on a road with a mountain in the background. I find this totally astonishing. I mean, this is not something that I would have ever guessed. On your cell phone, if you have Google Translate, and if you happen to be in Japan, you can take a picture of a menu, and it will translate it for you into English. Now, I have a friend who said that his son went to China recently, And what he would do is, deep learning has completely transformed speech recognition to the point now where it is really good. And so what he would do is talk into his Android. It would translate that into China and then would produce the Chinese sentence. And he would use it for taxi cabs and restaurants. And he said that it was almost like, the Star Trek Universal Translator. There it is in your hand. This is science fiction. It's really happening. It's really remarkable. But the most exciting thing, I think, is unsupervised learning. So it's now possible, you don't have to label anymore. There are unsupervised learning algorithms that you just need a lot of images. For example, these are called generative adversary networks. Now, the networks I've showed you are ones that you give it an input and you get an output, right? But these are networks that actually generate new things that, there's no input after the learning. It will generate new images. And I'm not going to explain how it does it. It does it by having an adversary. You have to distinguish between what's a real picture and what's a fake picture. And eventually it gets really good at making fake pictures. So after seeing many images of volcanoes, it spews out these. You have a couple control knobs, but every one of these doesn't exist. It just created it out of thin pixels, right? I mean, this is almost, it's kind of artistic because it's really generalizing what it is like to be a volcano, and it's creating new images that are in the same class. And you can do that for monasteries, you can do it for ants, you can do it for particular species of bird. So this is really exciting. Now, everything that has been done so far in deep learning is meant to model what goes on in the cortex. But there's a lot more to the brain than the cortex. There's a lot more to intelligence than pattern recognition, although it's bedrock important for performance, for survival. Now, there's another part of the brain which is just under the cortex. It's called the basal ganglia. And back in the 90s, we wondered what is going on down there. It receives an input from the entire cortical mantle, and then it projects back up to the cortex. So there's a loop, 100 millisecond loop. And it also projects to these dopamine neurons that are buried in the midbrain, and which project up, in fact, to the entire cortical mantle and to the basal ganglia. So these dopamine neurons, we know, are very important for motivation and for learning. They're part of the reward system. And Richard Sutton, who's an engineer, computer person, he came up with this actor-critic model back in the 80s. And the idea of the actor-critic model is that you compute what's called a value function. So the input comes in from the environment, and it's represented now, we know in the brain, in the cerebral cortex, which projects to the basal ganglia. And the value function basically tells you what's the likelihood of reward if you make a choice. If you take this as the state you're in, and you have choices, you can grab this, or you can grab that, or you can walk over here. Which of those has the most likelihood of a reward? It tells you the value of those choices, and then reports back to the cortex. And it was at that time that Peter Dayan and Reed Montague were postdocs in my lab, and they realized that this particular learning algorithm called temporal difference or reward prediction error could solve a problem, a very difficult problem, which is, what if you have to make a bunch of sequence of choices? Not just, right now, should I eat this or not, but, what should I do in order to be able to eat tomorrow or the next day to survive? And it turns out the temporal difference learning algorithm has been proven to solve that problem when you have a sequence of choices to make, and you don't get the reward until the very end, right? So it's delayed gratification. And what they did was to realize that these dopamine neurons might actually be representing the reward prediction error, which is the difference between the reward you actually get and what you expected. And based on whether you get more than you expected or less, you change the strengths of the synapses so that next time you'll have a better estimate. Now, this will be the only technical slide, but I just want to show you what the math looks like. So the idea is that the state at time t that you happen to be in, you take action A, and that transforms you to a new state, and you get some reward. And that continues on for many choices, many states, And then at the very end, you want to estimate what is the total reward you're going to get over into the infinite future, discounted by gamma, which is between 0 and 1. If it's 0, it means I'm only interested in the immediate reward. If it's 1, it means I'm interested in all future rewards. So this is the value function. It tells you the value of taking action at time t in state st. And you build this up through experience. And then your choice, it's called the policy, is to pick for a given state the action which maximizes this function. So this can all be implemented very easily, and there's signals that are in the basal ganglia which actually represent these. Now, okay, so what does the basal ganglia buy you? Let's lash the deep learning cortex onto the basal ganglia, a model of the basal ganglia, and see what it can do. Well, what it did in 2017 was to play the world's best Go player. Now, for those of you who don't play Go, it's the ultimate board game. It's 19 by 19, and it is to chess what chess is to checkers, just to give you an idea of the complexity. And in Asia, especially in China and in Korea, it is a very, very high art form. And the champions, the people who are, they're rock stars. They're like, LeBron James. Now, I gave a talk recently where I said this, and somebody in the audience said, "Who's LeBron James?" It shows you that every culture has its own heroes, right? And in any case, this was the AlphaGo had beat the South Korean champion in 2016, and Ki, who is the reigning Chinese champion in Go, he was very confident. He's a 19-year-old. He's really brilliant. AlphaGo can't beat me. So in 2017, after losing 3 games really badly, after humanity spent thousands of years improving our tactics, computers tell us that humans are completely wrong. This losing face in China is really serious because you suddenly let down your whole species. Now, what's remarkable is that this AlphaGo program, it had played itself hundreds of millions of times. Nobody knew how good it was until it played the world's best player. It made moves that no human had ever thought of before, brilliant moves that only later everyone realized that this is like rewriting the book. Now, these are things that nobody even knew about. It was creative. This is a creative AI. This is not just writing down rules and things that humans tell it. It actually is making discoveries that no human has ever made before. I'm going to give you one more example. Now, Go is good because it is a problem that humans have put a lot of time and effort into, and it takes a lot of practice and intellect to be good at it. But it is a game of perfect knowledge. Everybody sees the board, and nobody has any advantage. But the real world is a lot more complicated. The real world is uncertain. It changes. And in order to survive in the real world, you really have to be much, much more able to deal with new circumstances and generalize from your previous experience. And so I wanted to pick out a real world problem, see how far we can push this. All right? So here's the problem I picked out with Massimo Vergasola, who's a colleague of mine at UCSD in the physics department. So birds are known to soar, and the way they do this is by finding a thermal convection, which is an upwelling, and follow it up, and then they can glide to the next one. There are birds that migrate thousands of miles for weeks at a time without ever coming down by just going from thermal to thermal. Weeks, 2-3 weeks, from the northern latitudes all the way down to the equator. Here is an example of someone who actually instrumented a hawk with a GPS, and we're going to show you how that bird found the thermal and what it did when it found it. Oops. So the color tells you what the altitude is. So there it's looking for the thermal. It went down, it went up, it down, up, and there it is. It caught it. There's wind blowing to the left so that it's following the thermal as it's going up to the left. pretty good. I mean, that takes some talent. So the question is, can we learn to soar like a bird? Well, it turns out humans glide too. We have hang gliders, we have big gliders, and this is a sport. There are a lot of people who are very good at this. Michael Fee was telling me that he learned to glide like this when he was 14. Now, here's the problem. The problem is the atmosphere is not just a column of hot air going up. It's very turbulent. And we have to understand that turbulence if we're going to soar like a bird, because birds are in the real world. So this is what we put together, and this is something that came from the physicists. It's called Rayleigh-Bernard convection, and what you're doing is these are the differential equations that regulate the vertical velocity u and the temperature theta. And it's a convective problem that has to be solved numerically on a computer. And here is a simulation that Gautam Reddy did. So first of all, this is the look at the temperature field here. You see, it's not like it's a simple levels. There are these little spicules coming up, and then the vertical velocity here you can see is very turbulent and it's changing constantly. So this is a really complex environment to be trying to learn how to soar in. Here are in our model. Now we had a model in which in the computer it's simulating a flight using aerodynamic principles, and the two control parameters are the bank angle, mu, and the angle of attack, whether you're going up or down. And here are some of the things. We had a lot of sensors in the model. We had a vertical velocity center, a vertical velocity gradient, which turned out to be very important. And here is an example of where the velocity going up here is higher than here, which means it'll lift the wing on the left and tilt the bird. Then finally, a vertical acceleration. So this tells you that not only are you going up, but that you're going up faster. So here's at the very beginning, we have to give it many, many trials in order for it to get better and better. But at the very beginning, you can see it starts out here, and it's really good at going down. But after lots of examples and training, here's what it does. It takes a while, right? This is color-coded. The yellow and red is going up. And you can see it's kind of searching for the thermal, and it eventually finds it like that bird you saw. And once it hooks on, it does exactly what the bird does, a nice tight loops, and it goes up. And so this was, really a great example of how we think, you could actually discover something. The bird a model bird can perhaps use the same features. But we can do more. We can actually go in and ask, what is it in the model? Because we know what the inputs are. We know which ones were important for this performance. And so we can make some predictions. So here, and this is something we didn't guess, right? It just turned out this way. So first of all, the temperature had absolutely no value in learning. If you can take it out and there'd be no, almost all glider people think that, knowing the temperature is important because, of course, thermals are hotter air. So you think that would be important, but no, that turns out not to be important. The two most important features are the vertical acceleration and the vertical velocity gradient, A and tau. And in fact, if you put these two together, you get the best performance of all. And these other features, for example, control over the angle of attack, which is here represented by alpha. If you add alpha, it actually does worse. Right? So it's told us out of all the features, these are the two that you should pay the most attention to. And now, this seems like, we published this in PNAS and we got some interest, but, simulating something like this isn't the real world. I mean, it's a surrogate for the real world, but, let's see if we can actually teach a real glider to soar. And this is where Gautam got interested in a club in San Diego. This is in Poway, right? This is a suburb. And there's a club of people who do radio-controlled gliders. And it's a competition. They go out for the day and they see who can get their glider to go up, and they're controlling it with their RCs. Here's the glider. It's a 6-foot wingspan. It costs about $3,000. It's been instrumented as a GPS and has controls, and it can measure velocities and accelerations. And it took about a week of trials. And the way it works is really neat. They have a winch that catapults the glider up to about 100 meters. And then then you control it. And this was after the training. It follows the path and it finds the thermal. And this is in the real, this is in Poway. And it zips up, and at this point here, at 600 meters, 1,800 feet, it lost radio control. So it was automatically programmed to come down. But it did this about twice as fast as the other gliders that the humans were controlling. And of course, the humans couldn't feel it. Now, when we talk to real people, real glider pilots, here's what they tell us. They look for something called the bump. They're sitting in their glider, and suddenly they feel a bump. What is that? It's vertical acceleration, right? And the other thing that they say is, when the wing suddenly goes like that, I know that we're close, and so you steer it into the, it's like when you're skiing, you steer into the hill. It's exactly what this algorithm learns how to do. So this is really, I think, discovering something that has been known by birds for a long time and a lot of humans. So here's another example of a successful soaring field, superimposing it on a wide-angle shot. Now, the last thing I want to tell you about is another real-world example of where AI is going, and it's in social robots. This is a project that came out of a Science of Learning Center sponsored by the NSF that was based at UCSD, but involved 12 institutions around the world. And there were 6 of these centers, each one focused on something different. Ours focused on machine learning and neuroscience. So what we wanted to do was to take what's best known about learning in the brain and bring it into the classroom. And so here's the project. Javier Movellan is the person who created this robot called Ruby. And here's the first version, 1.0. And the idea is that this is a robot that's going to interact with 18-month-old toddlers, right? This is a preschool. And these little kids here, if you've ever interacted with them, they're frenetic, right? They run around like crazy. They pick up a toy, they play with it for about 10 seconds, and they throw it down, right? And so these very short attention spans. And so when they put this robot, by the way, it has 2 cameras, a swivel, it's expressive, the eyebrows go up and down. I don't know about the mustache, but it's meant to be interactive, and it has a Teletubby here. Okay. So here's what happened. They put this into the classroom, all ready to go. The boys run over to, what is this? And they grab the arm, they rip it off. Well, of course, little boys, what do you expect? So they go back to the shop, and the idea was, okay, let's put an industrial arm there, and we'll show them, right? We're going to really, they'll be able to pick the kid up, right? No, you don't have to do that. And so Marnie Bartlett Stewart said, I have a better solution. This is social engineering. So what happened was that they put a cheap pressure sensor, and when it went above a certain value, Ruby would cry. And the boys would back off, and the girls would go up and hug it. and the project was one revelation like that after the next. In other words, we thought we were going into the classroom, we were using science to improve things. No, the little kids were telling us things that we didn't know. And it got to the point where the little kids were so, Ruby was part of the class, and it was part of their social interaction. By the way, we learned that in order to get a little kid to pay attention and not throw it down like it's a piece of toy, is that Ruby has to react to them within a second. So if this little kid points to the clock, if Ruby doesn't look at the clock within 1 second, it loses interest, walks away. So that's the social engagement that you need. You need to be able to interact with the kid. And now this is 4.0. We were afraid that the teacher in the class would feel threatened because this is going to take their job away, right? We were a teaching robot. Quite to the contrary, it turns out that the teacher loved it because this is great for control. It was when otherwise the kids are all running around independently, but now they're, as you can see, gathering around Ruby. And so when the teacher has to do something else, Ruby is basically like an assistant. And so this is actually, it's happened over and over again in many, many of these applications. Something that was felt threatening, like it's going to replace the expert, the teacher, the physician. If you can do a diagnosis better than a physician, and the physician can use that information, he'll be a better doctor. He'll appreciate that. A lot of applications in medicine for reading x-rays, skin lesions, at levels that are better than the best doctor. And the reason is that we can teach the network with many, many, many more examples than any doctor would ever see in their lifetime, right? And that means that they can pick rare cases up that most doctors wouldn't have noticed because they just never were in Africa, and that's a very rare disease for someone here in the US. So this is something that the press has blown completely out of proportion. You know, that this breakthrough in artificial intelligence is not going to replace you or your job. It's going to make you smarter. It's going to make it easier for you. It's going to get rid of the repetition. You know, radiologists, do they really want to spend all day looking at these x-rays? No, they don't. They'd rather spend their time doctoring, working with patients. And if they can get an assistant that could read the x-ray better than they can, of course they're going to welcome that. They're going to help everybody. Now, at the last NIPS meeting last December in Long Beach, 8,000 people showed up. And there were 100 sponsors. I mean, this machine learning has become a very hot topic. At UCSD, the machine learning course, there are 400 people that took it. At Stanford, they had 800 people who took it. The starting salaries for people with a PhD is between $500,000 and $1 million a year, plus bonus. I'm tempted myself, I have to say. So I do some consulting, but the reality is that there's a real transformation that's occurring. And it's really big data. If you have more data than anyone else in a certain area, whether it's weather or social networking, then as Facebook has, then you're going to win. And of all places, who has more data actually that is accessible on the medical side is China. You know, they have 1 billion people there, and their privacy laws are much less than we have here. Our data is in silos, and it's very difficult to get permissions and aggregate the data. But in China, they're going to do that much faster and better than we can. So they're putting huge investments with billions of dollars that they're putting in training engineers and new AI labs, new support. Industry in China is they can do things really quite quickly. They can put up skyscrapers in a couple months if they want to. They just work around the clock. So this is something that's happening is really, really rapidly. Within the next couple of years, you're going to see self-driving cars. Well, already they're out there. They're being tested. But so many other areas of life. Now, the last thing I want to do, it's getting late, is to say that at the same time this revolution has occurred in artificial intelligence, there is a similar revolution that's occurring in neuroscience. And this is important because the current AI is based on what we knew about the brain 20 years ago. And now things are really, really shifting. Just within the last 3 years, you can see the change. Now, almost everything we know about the brain is levels diagram from molecules, the entire central nervous system. And there's structure at every one of these levels, but the one that we know most about is recording from single neurons with a microelectrode that you've already seen. Now, you record from 100 neurons, you write it up, and that's a paper. But there's 100 billion neurons. And furthermore, these neurons are talking to each other, so the information is distributed, it's represented in many parts of the brain. And trying to figure out how the brain works by recording from one neuron at a time is a little bit like looking at the world through a soda straw, one pixel at a time. Just think how difficult it would be to figure out what's out there, let alone having people running around and doing things, right? How would you follow them? All you see is the contrast in one pixel. it really is a tough problem. And a lot of progress has been made, but the point is, though, that it's very slow. And in 2013, Barack Obama announced the BRAIN Initiative, and this is a $5 billion, 10-year program. It's one of the grand challenges, like, for example, Kennedy's Man on the Moon project, or the war on cancer, or most recently, the Human Genome Project. And the goal here is to map the circuits of the brain, focusing on that network level, measure the fluctuating patterns of electrical and chemical activity flowing within those circuits, and understand how their interplay creates our unique cognitive and behavioral capability. This is a little capsule of a 150-page report that I helped write. A group of us, 15 of us, Corey Goodman, Corey Bargman, and Bill Newsom were the chairs, and we spent a year and a half on this. And so this is the first time I've ever had someone asked me to write a 10-year, $5 billion grant proposal. But it was hard because we had to set priorities. You can't fund everything. And there's already $5 billion a year at NIH for funding all the research in neuroscience. And so this has to be in addition. And so really the goal here in the BRAIN Initiative, we decided, was to have engineers partner with neuroscientists so that we can create innovative neurotechnologies. And that has happened on a grand scale in ways that I could have never imagined. It's now possible to record from tens of thousands of neurons simultaneously, from 3 or more areas simultaneously. And what we're seeing is something that could have never been seen with a single microelectrode. And I'm going to give you one example from my own research. This is a hypnogram. When you fall asleep, you go through different phases. You go into a deep, slow-wave sleep. The EEG changes from high frequencies to low frequencies, high amplitude, and you spend half of your time in stage 2, which is characterized by these mysterious sleep spindles. They last for about 1 or 2 seconds. They're about 10 to 14 hertz, and they're known to be coherent across the entire cortex. And there's a lot of evidence now that they're very important for memory consolidation during the night. And this means experiences you've had during the day are being implemented in the circuits within the cortex while you sleep. So that when you wake up in the morning, you're able now to integrate that information into your daily behavior. So I collaborated with Sid Cash, who's a neurologist at Mass General. And these are epilepsy patients who have grids of electrodes placed on the surface of the cortex in order to locate the seizure focus, which is where it starts. The idea is that if you cut that out, that this may, these are patients who have had drug-resistant epilepsy for many years, right? So this is the last step that they could take. And it's very invasive. You have to open the scalp. You have to place this in, and then for 1 or 2 weeks, the subject is just sitting there waiting for seizure, right? Because they're recording continuously. And we were able to get the data, especially during sleep, and to study the, you weren't supposed to see that, and study the patterns of activity during sleep spindles. Now, everybody thought it was synchronous across the whole cortex, and it's not. And I'm going to show you a recording, and let you decide for yourself. Okay, so peak is white, and the lowest is black, minus. So if you just follow the peak around, you can see that it's circular. It's a traveling wave from the temporal to the parietal to the prefrontal. Did everybody see that? So this is, we've done this now with a dozen patients with literally 50,000 spindles that we've analyzed, and about half of them are circular. The other half have other patterns, expanding patterns. Interesting, of the ones that are circular, 80% go in this direction, 20% go in that direction. And so what do we think is going on here? We have a hypothesis. We think that this has something to do with the information that is being activated in different parts of the cortex with different time delays, because there are long-range axons connecting different cortical regions, and there are time delays on those axons. And we think that those time delays are very important for regulating the traveling wave. Now, this is the caveat here, is that these are epilepsy patients, and we don't know to what extent the epilepsy may have something to do with it. By the way, this inspired us to Princess Leia. Do you recognize Princess Leia? right? You notice that she has these buns that look just like our traveling waves. Okay, so we collaborated with April Benasich, who is studies babies and infants. And this is study was done from 6 months to 18 months, high density EEG. And so we analyzed her data. And the beauty of the skull and the baby is it's very thin. So recording from the scalp is almost as good as having an electrode directly on the cortex. And so we got very high signal to noise recordings. And I'm going to show you what we saw. Now in the humans, we only saw one hemisphere, so you don't know what's going on with the other hemisphere. Here we have the whole cortex. So we were rotating the array at the same time that we're looking at these patterns. And as you can see, these patterns are flowing over the entire cortex. And every baby shows this. And it's a very, very powerful signal. So babies spend half their time sleeping. So they're really putting a lot of effort into absorbing the world and integrating that into their cortical circuits. Okay, now the last thing I want to show you is a Chinese curse. Now I told you that we've developed these instruments. The engineers have built things for us that are so powerful that we don't know what to do with them. They're so powerful. They're generating data at a rate that we can't possibly analyze. And this is an example of work that was done by Misha Ahrens at Janelia. And this is a zebrafish, and it has a genetically encoded calcium indicator. You can see outlines a nice brilliant flash whenever a neuron fires a burst of action potentials. The time resolution is about 100 milliseconds, so it's fast enough so that you can follow the activity as we look at the zebrafish. Now, the zebrafish is embedded in agar, so it can't move, and it's in the dark, so there's no sensory input. So we're dealing with a brain that is spontaneously active. There's no sensory input. There's no motor output, but you'll see that there's a tremendous amount of activation throughout the entire brain. So we're looking down here, we're looking from the front, we're looking from the side. There are about 80,000 neurons, and we can record 100,000 neurons. We can record from about 80,000. So it's just a 3D reconstruction with a very, very fancy optical system. Oops. Let's get this going. Okay, so this is the forebrain. This is the eyes here in front. This is the spinal cord. You can see things going up and down the spinal cord, midbrain. But what's going on? What does it mean? And there are these flashes every once in a while of high degree of coherent activity, flashing up and down the spinal cord. What was that? Maybe it was the zebrafish thinking, right? How are you going to go about analyzing this? This is intrinsic internal activity. Of course, this is happening in your brain all the time. When you're sitting there and just thinking to yourself, right, there's a spontaneous activity. This is you. This is the zebrafish. And that's the challenge. Fortunately, at the very time that we now can create these humongous data sets, we also have the ability to use machine learning to analyze them. So the very same deep learning networks are being used to analyze these recordings. And not just the recordings, it turns out that working out EM reconstructions using connectomics has been revolutionized by deep learning. It's now possible to automate that. So it's almost, it's much better than humans now in terms of the speed and the amount of data that you can reconstruct. And it's being used by genetics, people who are doing very large-scale genetic screens, large-scale genetic profiles. We saw Huangqi, for example, Zhang this morning gave us a beautiful talk from the Allen Brain Institute showing the tremendous amount of data they're collecting on connections and genes being activated in different parts of different neurons. And this is really, the data explosion is really happening in all the sciences at the same time. It's happening in physics, it's happening in astronomy, and all of those fields are greatly benefiting. Probably science more than any other area has benefited from now the analytic techniques that have been developed over the last 10, 20 years in machine learning. Many techniques, deep learning is just one of many techniques that are available. Bayesian networks, There's a lot of really excellent work that's being done on graphical models, and each one of these approaches is appropriate for each different problem that you have to tackle. So I mentioned I was on the NIH team. Francis Collins was the one who put together the team, and this photo was taken just a few minutes before he made the announcement in the White House, and he brought together some of the principal people that were responsible for the BRAIN Initiative, foremost Myung Chun, who is the science director, of the Kavli Institute, and Bob Kahn is the president, and she was the one who brought the white paper into the White House, and the president asked all of his cabinet members and secretaries, NASA, head of NASA, all of them to come up with a grand challenge project. And we were on the short list. Along with NASA, they wanted to bring an asteroid around the moon, which seems kind of neat, space cowboys. Department of Energy wanted to build a better battery, great project, but what can be more exciting than the brain? So we won. And I was really pleased to be there. I won't introduce everybody here except to say that just before this picture was taken, we were milling around talking to each other, and I was standing next to this woman, and I had no idea who she was, but she was very knowledgeable. She's an engineer, so I finally said, "What do you do for a living?" And she said, "I'm the director of DARPA." And that's when I knew that the White House is a great place to be if you want to network. Now, I was talking to her, and suddenly there was a tap on my shoulder. And I turned around, and towering over me, you have no idea how tall he is, unless you're there in person. And he came through this door, and so I was the first one he came up to, and I was flabbergasted. I had nothing prepared because of the fact that I was just, I didn't even introduce myself. I mean, how stupid can you be? And so all I said was, "Thank you, Mr. President." And thank you.